page here. It's time to move on. And it's a great pleasure for me to introduce Nick Delgass. Nick was one of the cadre that Michelle had assembled when I arrived. And as with many new academics, I formed many friendships with that group of students. And in fact, it's interesting for me because I know, of course, all of Michelle's students who've come through Stanford, and many of you who are students don't actually have that privilege. And anyway, it's like a big family gathering for me as well. It's with a great deal of pleasure to introduce Nick. The title of his talk is Mobility and Reaction of Sugars in Hydrated Zeolites.
It's a pleasure to be part of this Lumara Fest. Thank you for the invitation to participate. I've also been thinking how it is that 4 years of residence in Michelle's laboratory have translated so nicely into 25 years of enjoyment in the field of heterogeneous catalysis. It worries me a little bit, I guess, and makes me realize how long I've lived in Indiana, that my best explanation comes up in basketball analog. If you want to teach a novice how to play basketball, there are several ways you could go about doing that. One way would be to get a basket, set it up about this high, get a nice small light ball, and then start raising the basket a little bit and finally get them up to the point where they can actually make a basket under normal, legitimate circumstances. That is not my impression of Michelle's way. My impression of Michelle's way is more, there's the basket 10 feet high, there's the ball, go to it. And what you get from that is after many tries, finally getting the ball high enough, finally getting the ball in the net, then you get the elation of success under those legitimate conditions. To me, that's Michelle's gift to me. Continuing quest for that high standard. Now I should tell you that I have tried various forms, other forms as well, imitation. Some have worked better than others. The mustache was easy. I could never get the accent. I'm intrigued by symmetries in life as well as in science. I came up with a 30 as I thought back here too. I didn't realize it. It actually makes me feel good. It reminds me that Bob's a little older than I am. 30 years ago when he was finishing his PhD, I was just starting my PhD. And what I was doing was learning about a new nuclear resonance technique, trying to use it to study zeolite materials. What I'd like to talk to you about today is not so much a new technique, but a new nuclear resonance technique, for me at least, solid-state NMR. And I want to talk to you about an application of that technique to problems in zeolites. So it's a homecoming for me in a variety of ways, including that. So let me start. This is a collaborative effort, and I just want to point out that there are 3 different groups involved. John Brutzner is in the chemistry department at Purdue and is the NMR leader. George Sau is a biotechnologist and has brought us this sugar problem and some interesting opportunities for conventional catalysis, perhaps upstream in what has up till now normally been more biochemical, enzymatic-driven routes. And so this is our chance to look into that technology, and I bring to this group the catalytic expertise. Give you just a little bit of an outline of where I want to go. What's brought us to this area of sugars in zeolites has to do with an overall problem where we're interested in renewable resource conversion to fuels, particularly alcohols. And so you start with cellulosics or hemicellulose and try to take that to alcohol. The celluloses are polymers of sugars. You have to break those down by hydrolysis. and then you have to ferment them. It turns out that some of the alcohols or the sugars that you make along the way, hemicellulose, give you the 5-carbon xyloses, which are not easily fermented. If you isomerize the xylose to cellulose, then you can ferment that. And so there's an opportunity there for an isomerization reaction that would be useful. We've been particularly interested as we think about these kinds of catalysts to try to compare the behavior of the solid acids and homogeneous acids. In the cellulose hydrolysis, you start to break the polymer down and you end up with cellobiose, the dimer of glucose. And we have looked not with zeolites but with acid resins at converting that. And in that particular case, when I thought I had 40 minutes, I thought I would tell you a little bit about that. But I'll just tell you now the end result of that. When we compare the acid resin to homogeneous acid catalysis, so cellobiose hydrolysis, it looks like a proton is a proton. The rates within a factor of 2 or 3 are about the same, whether it's a solid acid or homogeneous acid. The problem I want to talk to you about today, the aldose to ketose isomerization, is a case where the homogeneous acid has essentially no selectivity, and the zeolites have some interesting selectivity for this reaction. So from a catalytic point of view, I think it's more interesting. There are some problems getting started with this. Problem number 1 is, can the sugars get into the zeolites? When we first wrote the proposal to do this, we were told by the reviewers that there was no way the sugar would ever get in. It was too sticky and would just go to the outside and that was the end of it. So we spent some time trying to prove that, in fact, it do get in, and I will try to convince you of that. We'll talk a little about the mobility and then about the reaction. This is the setup. If you start from cellulose and come down from that side, you end up with a 6-carbon sugar, which is glucose. In water solution, most of these sugars are very, very high concentration of the cyclic form. And so this is the normal form of glucose, and we can isomerize the glucose to this is an aldose, and then you can isomerize it to fructose to ketose. And it makes a couple of kinds of rings. It'll make a 6-ring or a 5-ring. These are furanoses and these are furanoses. With the 5-carbon sugar, we make mostly the furanose, and a little bit of the linear form is actually sticky for the xylose and the product. The key issue here, though, is going to be the fit. If we take HY with fairly big pores, and we look at a dynamic measure of the sugar size, and now the sugar size is sort of hard to measure because in the linear form, it might slip in some channels that it wouldn't be able to get into the cyclic form. And we're interested in trying to use that, but haven't really successfully come to that yet. We're pretty sure that in 4A, neither one of these sugars will go in. We're pretty sure that in HY they should go in, and I think I'll be able to show you that. It's a very tight fit in ZSM5. If you take this dynamic size of the molecule, it looks like it won't fit. If you build a model and try to fit it in, it just barely fits if you push on it a little bit. I think I can convince you when I get to it that we can actually get the sugar in there. I think, however, that the fit is so tight that the reactivity is not good for that, but we can talk about it. Now, first point is the question of can we get the sugar into the zeolite? And the way we want to look at that is to say, all right, we've got 2 choices. If we take a completely dry zeolite and we give it something akin to an incipient wetness or less amount of sugar solution, we know that the zeolite will imbibe the water. The question is, will the sugar go with it, or will the sugar be strained on the outside? If the sugar is strained on the outside and we just look at the numbers of things, what we find is that we'll end up with about a 50-layer coating of sugar on the outside. Okay? We'll make an M&M if there's a problem of this getting in here. All right? If the sugar goes in with the water, then we should have a homogeneous liquid-filled material, and we want to use MR techniques to try to follow that. So this is the stoichiometry that we think we have 2 choices. On the one hand, if the sugars don't go in, we're always going to see a solid-looking sugar no matter how much water there is because it's candy-coated. Right? If it's really going in, we may be able to get to a point where we can see some mobility due to the hydrated sugar inside the zeolite cavity. Okay? I won't show you too many amounts. It is interesting that if you do the incipient wetness experiment, the incipient wetness experiment tells you that it takes about 0.7 milliliters to fill up the pores and get the zeolite just wet. If you do the calculation, it's only about 0.4 milliliters. So there is a problem that the zeolite powder can hide water in crevices and things like that. We have to worry a little bit about exactly how, whether we do this interpretation right, but let me see if I can do this. Now, this experiment is cross-polarization, magic angle spinning NMR of C1 labeled C13 glucose in Y zeolite, all right? And we've done this imbibing experiment, and we'll take the calculated 0.4 milliliters per gram as the 100% loading amount, right? So that's what this is. This is the 50% loading. At 100% loading with this 2 molar solution, we should have 1 glucose molecule per supercage. Half a glucose molecule per supercage here. Now, in this proton-coupled experiment, we're not going to decouple the protons from the carbon, which would be a normal way of doing this. We're going to leave the proton field there, and if the sugar is immobilized and rigid, then I get this broad distribution of dipole-dipole interactions from the proton to the carbon, and I should see a line that's broadened to 25 kilohertz. And it will have some spinning side bands on top of that, and that's what this is. Okay? So this is the full dipole-dipole coupling of this random orientation of rigid sugar molecules, essentially. Right? And so that means at 50% loading, when I do this interaction with the zeolite, what I produce is an immobilized sugar. Now, whether it's inside or outside, we haven't settled yet, but it's not floating. It's not mobile. Okay? But as I add more solution, then I see significant amount of not liquid-like. It's still fairly broad. It still cross-polarizes, so it can't be a true liquid-like material. Right? But I see a significant amount. I still got this broad background, and we'll come back and look quantitatively at how these things compare. But as I increase the amount of loading, I get to a point where I can have mobile sugar molecules in the zeolite cavities, and so at 100% loading, too much of the sugar has been mobilized by the water to be accounted for any other way than to assume that the sugar goes inside. And to make a little confidence that the experiment really works, if we take the case where we don't expect the sugar to go in, and we again start at the 50% loading and then go up to 75 and go up to 100%, essentially the wide line stays there all this time. This is an M&M where all the sugar is on the outside and it has to be rigid all the time. The water can go inside the cavity, but the sugar can't. Okay? So we think the sugars go in. Now the answer, the question is, what's the nature of those sugars? One thing we've seen is that at low loadings, at 1 sugar molecule per 2 supercages, and each supercage half filled if the water is really completely distributed uniformly. Right? What we have is something that we're going to call a chemistor sugar molecule. It has a long enough residence time on the surface that it looks like it's immobilized to the same experiment. And now I'll show you a series of NMR experiments now which will try to prove to you that in fact this chemistor immobilized sugar exists, and then we have at least 1 and probably 2 other mobile states that coexist with it. Now what we're looking at is still a magic angle experiment, but as a function of cross-polarization time. And again, for rigid material, the coupling between the protons and the carbon is very strong. There's an efficient cross-polarization, and so you build up signal very quickly. And what we see at the 50% loading is we get a maximum, and the signal as a function of cross-polarization happens about a half a millisecond. And this is indicative of a fairly mobile species. Sorry, immobile species. If we go to the 100% loaded material, what we see is something interesting that was not so easy to see in the last slide. If you look at the fat part of the curve, where the valleys come to, okay, what you see is a maximum that looks not very much different from the 50%. Okay? The maximum in the broad part of the curve still comes at about 0.5 milliseconds. But if you look at these spikes, all right, which are considerably the thin part of the dynamically narrow part of this curve, These are the alpha and the beta forms of the sugar. What you see is there's this one gets bigger, this one is fairly large too. Between 2 and 5 milliseconds, there's another maximum of the narrow part of the sugar. That's the mobile part of the sugar, which doesn't cross-polarize sufficiently, and so we have two different states here. What you have to remember is that we don't have sorted out exactly how they communicate or not with each other, or why they don't. But if this mobile sugar and immobile sugar are together in this same core structure, they are not exchanging fast, because if they were exchanging fast, you get average anymore characteristics. There is this state that's mobile and this state that's immobile. One more peek at or proof that in fact we have this kind of state. Another way to look at that dynamics is to start doing the decoupling and the proton decoupling with the carbon, and then interrupt that decoupling for a certain time period, and then turn it back on again to do the measurement. And if you have a rigid material and you turn off the decoupling, what happens when you turn it back on again? Everything is out of phase, and the solid rigid part goes away in this experiment, and the more mobile part is what's left behind. And so we have the same picture we had before. 50% loading, we said it was mostly immobile. In the interrupted decoupling experiment, the signal goes essentially away. That means everything is really immobile. At 75% loading and 100% loading, we do have some rigid material, but about half the signal comes back in this interrupted decoupling experiment, again showing us the mobile and the immobile part. If we look at the relative amounts of this chemisorb immobilized material at different loadings in Y zeolite, what we're looking at here now, I've gone back to the coupled experiment. Shorthand for this is cross-polarization, no decoupling. John keeps reminding us that no decoupling is coupling, and so this is the proton-coupled experiment, okay? And what you see in this broad part here, that's the full dipole-dipole splitting of the broadening of the rigid material, and there are certainly some differences, but the areas under the curves in this low part here are the same order of magnitude, within a factor of 2. Actually, the calculations say they're within a factor of 20% of each other when they're properly normalized. So what that would suggest is that there are sites that will trap the sugar and hold it fairly tightly, and then in addition to that, as you add more water, you have some extra molecules that will float. I have a deuterium version of that as well, but I think I won't take the time for that. Now, there's two other aspects that I want to talk about, and something that we're intrigued about. Eventually, we want to look not only at these reactions, but other reactions that can go on as you begin to increase the temperature. And one of the reasons that we were slower with the ZSM5 than we were with the HY is because in ZSM5, this is the alpha-beta glucose, and this is a peak that took us quite a while to understand. This actually is 1,6-anhydroglucose. So now, if you take ZSM5, you have a situation where you have a fairly high silica to aluminum ratio, you have an increasingly hydrophobic surface. We have a reasonably tight fit. I'm not going to show you all the same evidence that I showed you for the Y zeolite, but we have similar kind of evidence that shows that in fact the sugar does get into the ZSM5, and it does have a chemisorb state and this more mobile state. Right? But in addition, it has this anhydroglucose state. And that organic chemists are going to cringe at my bad stereochemistry here, but this is supposed to be a chair, and this is the 1 carbon, and that's the 6 carbon, and that's the extra dehydration that makes this extra ether linkage, in addition to this Pyrenees ring that comes from here. So what happens in the hydrophobic zeolite is that zeolite encourages this dehydration reaction. You see the same phenomena in ZSM11, again with a high silicon to aluminum ratio and hydrophobic surface. So we're just sort of getting started at looking at some of these reactivities, but we're interested in not only the acidity, but what role this hydrophobic surface might play in getting things going. I'll show you one aspect of the reactivity. That's sort of the bottom line for where all this stuff is going. This is not a complete data set, and it's a little bit of apples and oranges, a funny kind of comparison, but there are two main points to get from this. If you look at, this is NMR data where we actually can warm things up in the NMR tube and follow the reaction by watching the glucose and fructose and xylose directly from their NMR signals. These are more standard autoclave kinds of experiments with HPLC detection. The rates are the same order of magnitude in those two measurements as you would expect them to be. If you compare these two, glucose and HY and xylose and HY, here you see that even though the temperature is higher for glucose, the actual rate is higher for the xylose, and that's what you expect. Xylose is an easier isomerization than glucose, and we see that. But the most interesting thing is that if you try the xylose isomerization in homogeneous acid, if the acid pH is too low or too high, then nothing happens. If the acid pH gets low enough, then the sugar chars. And we have never been able to create a condition where we get any selective reaction to occur, and so that makes the reactions of the zeolites pretty interesting. Quick conclusion here. We think that the glucose and xylose enter the Y zeolite cages, but not A. We think the sugar exists in 3 states. Now, I told you about the bound state. We talked a little bit about that free exchanging state. I forgot when that thing went by. There is in the proton decoupled measurements a narrow enough line to show J coupling on some of the most hydrated zeolites, and that looks like an even, it's a narrower line and even more mobile line than this exchanging material that we saw in the CP. The occupation of those states depends on the loading. If you go to the hydrophobic zeolite, you can see an extra reaction in ZSM5. Reactions occur, but the zeolite is significantly more reactive than the homogeneous acid, and these are aspects of the system that we will pursue further.
Time for some questions.
You indicated that you're talking about hydrophobic ZSM5, but have you tried the non-hydrophobic, the higher aluminum content?
We haven't. We will. We're going to try to go both ways with that. We would like to look at some ZSM5 with a higher aluminum content, but we'd also like to de-illuminate some Y and see if we can drive the Y to a high silicon to aluminum ratio to do the dehydration.
I was thinking of an alternative explanation rather than the hydrophobicity. That is just the shrinkage,
There is a little bit of a change in size.
volume change.
That's right. There's a change of size in the molecule, which may be important. It also, in the process of closing that extra ring, changes the orientation of the OH groups around the ring. So it is a slimmer molecule with a different kind of external surface, and that's the third role as well.
Any questions?
Nick, what is the role of acidity here?
Well, these are reactions that are acid catalyzed. That's what the literature says, even though we aren't able to make them go in the normal homogeneous acid medium. So the isomerization is catalyzed by proton transfer.
Is it a frosted?
Yeah. That's the
And so
theory.
you looked at the role of acid strength.
Well, we're just getting into that. That's yes, we will. We have not, but that is one of the things that we're interested in. And actually, it raises some interesting questions for us. There's a very good understanding, or a reasonably good understanding at least, of acidity for vapor phase reactions when you have a proton that sits there, maybe hops from site to site, but when the molecule comes down, there's a direct contact between the proton and the molecule to react. In these reactions where you have water, the proton can be hydrated, the proton can be tethered to that site in a sense because of the charge exchange. The molecule itself may be hydrated or partially hydrated depending on how much room there is. The definition of acidity and the role that the solvent plays in these liquid-filled pores, I think, is going to be different from the vapor phase stuff, and we're just starting to try to
coffee, I'd invite you to share in the discussion privately with Nick in this meeting time. Let's resume promptly at 5 minutes after 11.